All right, y'all. Today we're going to be talking about graphing exponential and another kind of function that you can probably see in the title, but we'll get to that here in a little bit. But we're going to start with exponential functions because it's ones that you should be familiar with. So I want you to try and see how much of this you can graph on your own using a calculator. But our exponential functions, just as a reminder, is our y equals a times base b to the power of x. And so we call it an exponential function because it has that x in the exponent. And the one that we're going to focus in on today, obviously this is kind of our general form, is I want to focus in on f of x equals 2 to the power of x. So go ahead and use your calculator. You can use Desmos or you can use your TI-84 to graph that function f of x equals 2 to the x. You can graph it over here on the right. You can pull out some values from the table if you need to, and then try and see which of these key features you can kind of figure out on your own. I'll go over all of this here in just a little bit. All right, y'all. So for our graph, we should have seen that we have a point right here at 0, 1, 1, 2, 2, 4, 3, 8. And our graph curves up to the right through these points. And to the left, it gets really, really flat, and it almost looks like it reaches 0. But if you remember from exponential functions, they do not actually go through or cross or equal 0. They get really close to 0 without actually going through them. Okay? So this graphing point that we see right here, it's going to be that y-intercept. So 0, 1. And it's not always going to be the y-intercept for our parent function, though. It is that y-intercept. Our horizontal asymptote, like we said, is that y equals 0. And then, of course, our domain, looking at this exponential function, it continues forever towards negative infinity. To the right, though, it actually is going to continue forever. I know it looks like it steers straight up right around 3, 4-ish, but it would keep going forever. We could plug any number in for x. So our domain would be all real numbers in set notation. We could also do negative infinity to infinity in interval notation, or negative infinity is less than x, which is less than infinity in inequality notation. Then lastly, for our range, we're going up forever. That's clear, but we do stop at that horizontal asymptote of 0, and we don't actually equal 0. So we'd put parentheses 0 to infinity because we don't actually equal that 0. Or, of course, we could just say y is greater than 0 in our inequality notation. Okay. So most of this should be pretty clear, and it might even feel familiar from what you've kind of done in Algebra 1 with exponentials before. So let's kind of play with our exponential just a little bit. We're going to not focus a lot on transformations today, but I do want to kind of get us a bit more comfortable with this graph. So let's look at some transformations. So if we have y equals 2 to the power of x plus 2, we can clearly see that our transformation, that plus 2, is going to shift our function up by 2. So how that would change it is our graphing point, instead of being 0, 1, would now become 0, 3, and our asymptote would be y equals 3. Or not y equals 3, sorry, y equals 2, because it shifted up by 2 from 0. So we can go and add those onto our graph. So our asymptote would be right here at 2. Our graphing point would be right here at 0, 3. And then I can just repeat that same pattern that I got on my parent function to get a few more points for our exponential function. But in general, it should look like the exact same shape, just shifted up by 2. Finishing things up, our domain is all real numbers because nothing's really going to change that. Once our domain is all real numbers, it's not going to be any different. No amount of shifts or stretching or anything is going to change that. But our range shifted up by 2, so it's now 2 to infinity instead of 0 to infinity because we can't go any lower than 2. Okay. Now let's look at number 2. Number 2 is a little bit different. This one is negative 10 to the power of x minus 1. So some things that are different. We have a negative out front. Our base is 10 instead of 2. And then our exponent this time is x minus 1 instead of just x. So that negative out front, that's going to cause a reflection across x. And that minus 1 in the exponent, that would cause a shift to the right by 1. Okay? And Our base being different, it's not a vertical stretch. I don't want you to get it confused by that. It's really like we have a different parent function. So I want you to think of number 2 as building off of the function y equals 10 to the x. And that function y equals 10 to the x, it would have the same parent function graphing point because that 0, 1 comes from plugging 0 in for x. And of course, 10 to the 0 would equal 1. So our graphing point is still 0, 1 for 10 to the x. So how would this graphing point change? Well, I've shifted it to the right by 1, so that instead of 0, it's going to be 1. And I reflected across x, so instead of positive 1, it would be negative 1. So our new graphing point would be 1, negative 1. And our asymptote, we didn't shift up or down, so it's going to be that parent function asymptote of y equals 0. So now we can go ahead and add in our asymptote and our graphing points. Our asymptote's at 0. Our graphing point's at 1, negative 1. So we can pretty clearly see we've shifted to the right by 1, and we're now on the other side of our horizontal asymptote because of that reflection across x. And if I wanted to get another point, I can just plug in 2, or, I could plug in 0 if I wanted to. But let's plug in 2 real quick. So negative 10 to the 2 minus 1. 2 minus 1 would be 1. So that gives us negative 10 to the first. Anything to the first power would be just 10. So that would give us negative 10. So 2, negative 10 would be another point we can use. And so we can see that this one's pretty steep compared to our 2 to the x. So the big thing you should notice is, of course, 2 to the x, our points are pretty close together because I'm multiplying by 2. For 10 to the x, our points are really far apart because we're multiplying by 10. Our next point after this one would be negative 100, which is super, super big, and not really anything that we're going to be graphing. So we really only need those 2 points when we're worrying about y equals negative 10 to the x minus 1. And sometimes really just the 1 point, if you can at least get the graphing point and then do the general shape of the exponential function, that should pretty much cover and show me that you really know what you're doing in terms of transformations and everything else. Okay, so let's finish out by talking about the domain. So just like we talked before, that domain of all real numbers, never going to change. Even though we have transformations, I could still plug anything in for x. Our range, though, this time we reflected across. So instead of 0 to infinity, this would be negative infinity to 0. And important, y'all, we always go from least to greatest. So that's why it's negative infinity to 0 instead of 0 to negative infinity. I know it's weird because you want to go like, oh, well, it's 0 going down, but we still always write it from lower value to higher value. So that's why it's negative infinity to 0. Hey, our very last one is the weirdest one we're going to see today, and it is base E. Okay, so base E, if you were to type E in your calculator, E is equal to about 2.72-ish. Of course, if you typed E into your calculator, y'all, and you saw that, just like pi, E is a number that we kind of treat almost like a variable, but it is still a number. Okay, it's a much longer number than this. It has a never-ending decimal place, but we can kind of think about it as 2.72 or about 2.7, really. And the reason why E is important is because E is called a natural number. And that natural number E, it has a lot of applications throughout science and mathematics. It shows up in a lot of different ways. So that's why we do focus in on E as one of kind of our exponential pieces that we explore a bit, is because it is really important. We can use it to calculate a lot of things. It governs how a lot of stuff grows or operates or reacts. Kind of like pi. Pi is very useful throughout all of mathematics when it comes to circles. So just kind of something to keep in mind. When you see E, it's that 2.7-ish. We'll talk a little bit later when we get to the application piece of exponentials and that other function, where E is really important and where it comes into play. But for now, just know E is the natural number. It is an important number, and that's why we focus on it. But let's look at some transformations real quick. So first and foremost, we have that 2 in front. That would be a vertical stretch by 2. And then this negative 1 in the back, that would be down by 1. So our graphing point, Just like how y equals 10 to the x, the graphing point is still 0, 1. If we had y equals e to the x, same thing, because e to the 0 is still equal to 1, our graphing point is still 0, 1. So when we're thinking of how that point's going to be transformed by our transformations, a vertical stretch by 2, we'd multiply that by 2, so 0, 2, and then we are shifting down by 1, so we're actually still at that graphing point of 0, 1. Now, what is also going to change is our asymptote. Because we shifted down by 1, our asymptote is down to -1. And you might be thinking, Mr. Arbone, how can our graphing point still be 0, 1 if we had some transformations? Well, when we put it with our asymptote, I think you're going to see why it turned out that same way. So our asymptote here is -1, and our graphing point would be 0, 1. So as you can see, even though we still have that parent function graphing point, see how it's 2 away from the asymptote instead of the 1 away that we got on number 1 and number 2? That's because of that vertical stretch by 2. So we're still stretching it out by 2. It just happened that because we shifted down and then stretched by 2, it ended up being in the same spot it would have been if we didn't do anything at all. But because of our asymptote shifting down, we still get that vertical stretch by 2. Okay. Now, for the rest of our values and our points for E, y'all, one of the things that's obviously difficult about E is that a very simple number to plug in or find the powers of? Not really. So as long as we have this graphing point, y'all, that's really all we need, because we already know the rest of this graph is just going to kind of keep that same shape. If you want to find the exact values for E, we can use our calculator to find those, but we don't need to use our calculator, or we don't need to find those by hand, because technically, like if I wanted to plug in 1, then I would get 2 times e to the first minus 1, which would basically give me 2e minus 1. I can't do that without having a calculator. I mean, I could kind of guess around 2.72 times 2 is about 5.44. And then minus 1 would give me about 4.44. So we can kind of guesstimate. So about 4.44. So I didn't do a very good job of sketching mine. But I don't want you to worry too much about getting exact points when it comes to E, as long as you can calculate that graphing point. That's really the only one that I'm concerned about. If you can get the graphing point correct, then the rest of the points we're really not too worried about. Okay, so last but not least, let's talk about our domain and our range. Domain, still all real numbers. For our range, we've shifted down by 1, but we're still going up, so -1 to infinity. Okay, and like I said, y'all, I don't want you to worry about the points too much today. I just want you to kind of think about how, even though our base changed, we still have that same exponential shape. As we change our bases, it just changes the sharpness or the steepness of our exponential, but we could also change that with the vertical stretch as well. So exponentials don't play as nice as some of our other functions that we transform, but a lot of our transformations, our A, B, C, and D values do still apply. We'll dig a little bit deeper into transformations next class when we talk about transformations of exponentials, and in the class after that when we transform our other function. But let's kind of take a different direction and let's find what that other function would be, because this has told us a lot about exponentials, but exponentials has a partner. Just like everything we've been talking about in Algebra 2 this year, y'all, it has an inverse function, or has a function that goes with it. Our quadratic, our parabolas, has square root. Our cubics have cube root. Our rationals have other rationals. So every function we have has that inverse function that goes with it. Even a linear has an inverse that's another linear. An absolute value has its inverse, which isn't actually a function, which is why we don't really worry about it. But we have this partnership. So as a reminder, if we have a function that has the ordered pair x comma y, its inverse would be y comma x. We would just switch that x and y, switch that independent and dependent to find those new points. Okay. So what I want you to do, and I'm going to let you do example 1 on your own, is that I want you to graph f of x equals 2 to the x. We already have the graph, so I just want you to fill in the table. Let's go from -3 to 3, not -1. So I want you to use your calculator for this, y'all. Fill in this table of values for 2 to the x, and then take that table of values and switch the independent and dependent to get your inverse points, and then graph those inverse points on this graph over here to the right. Once you have graphed everything, we'll talk. You can unpause me, and then we'll talk about that inverse function and what it kind of looks like. Okay, so go ahead and do example 1 on your own. All right, y'all. So let's talk about this original function, this inverse function. So hopefully you got similar points to me to 2 to the x. When we inverse it, we're just switching those x values and those y values. So our -3 to 3 becomes our y values for our inverse functions. Our 1/8 to 8 becomes our x values. And when we plot these points, we can see a very similar looking function in terms of shape, but of course it is that reflection across that y equals x line like we know our inverses to be. That gives us this new function here. And it's very similar, except our original function, it kind of looks like it flattens out at the x-axis, our exponential. This new function, it looks like it flattens out at the y-axis. So similar traits, but just a little bit different. One thing that we kind of want to cover is the inverse of f of x equals 2 to the x a function? So is this new function we've gotten, our one here in blue, is it a function? And it would be, because it passes the vertical line test. We also could have known it was going to be a function because our original function, 2 to the x, passes the horizontal line test. And then we also know it is a function because it's 1-to-1. Every x value has a single y value. So our function is a function. We're all good to go on that. So let's look at some key features and kind of see how these two functions compare. So our exponential function's domain was all real numbers, and its range was 0 to x. So for our inverse function, its domain would be that 0 to infinity or greater than 0, while the range is going to be that all real numbers. And we can kind of see this on our graph, how it's stopping at that 0 in the x direction. So that's why its value is greater than 0. But it would continue forever in both directions, up and down. Now, for our intercepts, it actually has an x-intercept instead of a y-intercept. So same thing, similar, but slightly different. And it has a vertical asymptote instead of a horizontal asymptote. So it has the intercept 1, 0 and the asymptote x equals 0. And then it does increase from left to right, just like our standard exponential function does. It doesn't increase quite as fast, kind of almost like that radical shape where it's kind of that square root function, but it is still increasing from left to right. And we're not going to worry about end behavior, y'all. I know it's here on the notes, but it's not really a thing that we cover in Algebra 2. You'll talk about end behavior more in pre-calculus. All right? So let's give this new inverse function an actual name, and we actually call this a logarithm, which some of y'all have probably been like, why does he keep referring to it that other function? It's logarithm. That's what the notes are called. So we do call this other function a logarithm, and we write a logarithm as y equals log, for short for logarithm, with our base of b and then of x. So we read this as y is equal to log base b of x. So base, then of, because that x is inside the logarithm. Okay. And if we have an exponential y equals b to the x, then our inverse logarithm would be x equals log base b to the y, because remember they have that inverse relationship. But you can see that b and that b is the same. Our base between our original and our inverse is that same base. So we can kind of see this in action. If my exponential form is y equals b to the x, my logarithm would be x equals log base b of y. So another way to think about it, if I have 16, that would be equal to 4 squared. Writing that as a logarithm, 2 would equal log base 4 of 16. Okay, so if you notice, 2 and 2 are still there, 16 and 16 are there. 4, which was the base of my exponential, became the base of my logarithm. So thinking the other way around, 3 equals log base 10 of 1,000. If I move this base over to the other side and made it the base of an exponential, then I would get 1,000 is equal to 10 to the third. You might notice that's still a true statement, just like our other one. 16 equals 4 squared, 1,000 equals 10 cubed. So I can switch between exponentials and logarithms because they're inverse of each other. Just like I can switch between a square and a square root, and I can switch between multiplication and division or addition and subtraction. We're doing that inverse operation. So go ahead and pause me real quick, y'all. See if you can rewrite D and E into their component form. All right, y'all. Now, last but not least, our 32 equals 16 to the 1.25. That would be the same as 1.25 equals log base 16 of 32. So that base 16 is shifting between the exponential and the logarithm. And then last but not least, if we have a equals b to the power of c, that would be the same as c is equal to log base b of a. So that base b is shifting between that exponential and that logarithm, while the a and the c either are inside our log or our c, which is up as our exponent. So the last thing I want you to do is I want you to think for our functions y equals b to the x and its related log function x equals log base b of y, think of what restrictions we could have on those variables. So think of what can I plug in for y, what can I plug in for base b, and what could I plug in for x. So think of their graphs, think of their domain and range, what are some values that worked for each of them, and think about what restrictions you might have. So go ahead and pause me, try and fill these out to the best of your ability, and then I'll... All right, y'all. So for our variable x, remember x for our exponentials, it's what we plug into the exponent. So our variable x, we can plug anything in for x. For our exponentials, we know it has that domain of all real numbers. Okay, so for my log, because we switch that x and y, and x is actually what our log function would be equal to, our log function can equal any value, just like we can plug any value in for our exponent. So we can input any value in for our exponent. Okay, for our base of b, we don't want to have a negative base because think about it, our base is what we're multiplying by each time. If I'm multiplying by a negative number, it's going to switch my y value every single time that I multiply, and that's going to make a really wonky, non-connected graph as I go from point to point. So we can't have that negative base. It's not actually going to create an exponential or a log. So likewise, I can't have a negative base for my log. If my base can't be negative for my exponent, it can't be negative for my log. And then last but not least, for our y value, so y value is our range in our exponential, and we know our exponents stop at 0. They can't become 0 because if I'm taking something to an exponent, I'm always going to get a value out. I'm not going to get anything out that's negative. It's always going to be positive, so it can get really big or it can get really, really small, but it never equals or crosses 0. So because my exponent can give me any value above 0, same thing. My logarithm, I can plug in any value bigger than 0, but I can't plug in 0 and I can't plug in negative numbers. You can test this out if you go to your calculator. So let's go to our calculator now. And let's just we'll use our log button. So if you notice, this log button is this one right here. And let's just take the log of any negative number. So let's say the log of -5. And if we hit enter, you'll see we get this answer, non-real answers. So all calculations must result in a real number. So we can't actually get that answer when we take a negative logarithm because we can't actually get those negative numbers because our exponent can't go past 0. And because they're related, they're attached to each other, that's going to kind of follow through as such. So I know that's kind of confusing for right now. We'll talk about it a little bit more when we get to our transformations of exponents and logs. But just kind of bear with me for today. Think of today more as like our exposure to exponential and logs than our like mastering of them. Okay. So we have already talked about our logarithmic function, but we have two special logs, and you might have already noticed them on your calculator. But they're a log with base 10 and base e. So if we have a log with base 10, we actually call that a common log. And it gets the name common log because it is the most used logarithm. And because it's used so much, we write it a little bit more casually, and so we just write it as log. So if you ever see a log without a little base underneath it, that means it is a common logarithm, and you need to remember that its base is 10. Now, the other log that we use all the time, it's nearly as common log, is a base with our natural number e. And because it uses the natural number e, we call it the natural log. And this one, we get fancy and we change the normal log to be ln, which stands for natural log. And once again, we don't write a base with it because if you see that ln, we are implying that its base is e. Okay, so down below, we're going to kind of see what these graphs look like. So we've already graphed log base 2 and log base 3. And we want to graph our common log, so log base 10, and our natural log, which is our ln. Base e. So what I want you to do is I want you to use your calculator and graph both common log and natural log and add them on to your sketch right here. So I'm going to remind us. So in our calculator, we go right here to y equals. Well, after I get out of this. Okay, we go here to y equals, and we can type in, so like log, and then hit x. And then we can do natural log, which is right under log, the ln, and then hit x. And then we can graph by hitting that graph and then going to the table. So go ahead and do that real quick for me, y'all. And we will go over what these graphs are going to look like, okay? All right, so hopefully you got something looking like this. You might not have the exact same points that I have. I kind of pulled them out from the table to the best I could. But what you should have seen is that our natural log kind of lands us in between log base 2 and log base 3. And that makes sense because remember that natural number e, it's about 2.7-ish. So it should land somewhere between log base 2 and log base 3. Our common log base 10, you can see it flattens out way faster because it's shifting by that power of 10. So it goes from 0 here to 10, 1. And then if we did another point, it would actually be at 100, 2. Just like our exponential shoots up really fast, our log with higher bases shoot to the side really fast. Okay, so if we had logs with lower bases, like a base of 1.5 or a base of like 1/2 or a base of 1/8, it would be much less, I don't know if steep is the right word, but much less flat. It would be going up more. Almost like a stretch, but remember with our bases, it's not really like it's stretching or compressing. It doesn't really follow those rules, the same thing. It's really like it's changing kind of the base. It's like multiplier, if that makes more sense. Okay, so the last thing we're going to talk about, y'all, is this natural log and common log. They do have companions as exponential functions. So what would the inverse be? We already found the inverse to 2 to the x when we graphed it earlier. So if we have y equals 2 to the x, our inverse function would be log base 2 of y equals x, or just y equals log base 2 of x. So what would our inverse function be for our common log and for our natural log? Well, for our common log, our base is 10, which means our inverse function would, of course, be y equals 10 to the x. It would just be that same exponential, but with a base of 10. And then likewise, for our natural log, our base is e. So our inverse function would be y equals e to the x. So that is why we are focusing on those three bases, base 2, base 10, and base e. Base 2, because it's going to be the easiest to work with when it comes from a transformation standpoint for exponentials and for logarithms. And then base 10 and base e, because of how important they can be for logarithms, we're going to also work with them for exponentials. So we're going to focus in on base 2, base 10, base e, analyzing them, key features of each, and then, of course, our transformations, working with all those functions. So that is all I got for today, y'all, on graphing exponentials and logarithms. If you want to learn a little bit more, we'll talk about transformations with both of these a little bit later.